Okay, so we should see a little red flashing light in the upper left-hand corner of our Zoom windows, which indicates that we are recording. And with that, I will turn the floor over to group 3 and let them share with us their presentation.
Oh, yes, and welcome and thank you for coming to Group 2's presentation. Group 2 consists of Andrew Buchanan, Mary Alice Clank, Matteo McKinney, Henry Pham, Gabriella Ramsey, Austin Sharp, Mohammed Taha, and Andrea Wright. We put all of our minds together throughout the course of the semester to come up with MECR, the Multiple Environment Cell Culturing Reactor. Our entire device, to meet all the customer needs, had 8 different subsystems. The first is the user interface, which is easily controlled through an iPad and is the brains behind our entire operation. There are controllers throughout the entire design to move every part autonomously. The structure and enclosure is what encloses all of this. It is made out of aluminum tubing and acrylic glass. It is also a BSL2 biosafety cabinet of a Class 2 Type B2. There is also material transport, which uses a rack and pinion for 2-axis movement, as well as a lead screw motor for Z-axis movement. On top of this material transport, there is a cap remover, which removes caps from the tubes through a twisting motion, as well as removing weld plate lids by having the user previously attach caps to the weld plates. So it just grabs the cap and removes it. On the material transport is also the liquid dispensing device. The liquid dispensing device uses a stepper motor and a lead screw to get very accurate pressure differences to move liquid from and inside and out of the dispensable pipette tips. Next is our climate control system. Zooming in on that, there is 4 different compartments here, all of which are independently temperature controlled and all have independent gas control as well, through a diffuser and a pressure release valve on the back. The main reason for having all these different containers is for our measurement devices. There's 3 different styles. There's the tube measurement device, which is essentially the same design, but just spaced out a little bit differently for the 15 and 50 milliliter tubes. There's also a 384 measurement device, as well as a non-384 measurement device, which provides ODFI measurements for all the other well plate sizes. Finally, our last subsystem is the plate movement, which achieves 3 types of desired motion: the linear, the orbital, and the double orbital. The linear motion is achieved through a stepper motor and a screw. The circular is achieved through a motor with a radial arm attached to shake it in the orbital. And when engaging both of these, we can receive the double orbital pattern. All of these designs came together based off our the main driving concepts. Next slide. The main concept that drives it is our economic engine. We wanted this to be super cheap so that many laboratories could afford it. And mainly, we wanted to be under the $10,000 budget provided to us. We were also very passionate about having high quality equipment. Getting sent home labs was very interesting for all of us, and we realized the importance of having a high quality equipment. And so we became very passionate about that. And after researching more about the bioreactors, we found out how just task consuming it really can be and just how much manual work it is. So we became also quite passionate about making it fully autonomous and capable to do everything on its own. And so this decided, okay, well, what can we be best at? And so we decided to put all of these, we wanted to be best at culturing cells for as long as possible. And to do this, we had to make a very cheap plate measurement device, or a plate movement device, a cheap measurement device, as well as cheap gas and thermal control, as these were in each of the different climate control systems. So combining all of these is how we got to our MECR design. Mary Alice is actually going to break down our first subsystem, the measurement subsystem.
Yeah, thank you, Austin. As Austin stated, our design maximizes independent simultaneous testing. To accomplish this while also minimizing culture exposure to the atmospheric conditions outside of our climate control chambers, each chamber has to have its own measurement system. Each chamber has a unique measurement system designed for the well plate or tube size that it holds. One enclosure exclusively incubates 384 well plates. For this system, a line of 16 LEDs is moved across the long side of a 384 well plate by a belt and pulley system. These 3mm LEDs produce a 600 nanometer wavelength. To take optical density measurements, the LEDs are positioned directly above the well centers of all 16 wells in each column on a 384 well plate. The light passes through the cultures and is absorbed by the 384 diodes in an array below the well plate. For fluorescent intensity measurements, the cultures are excited by the LED light and reflect a different wavelength that passes through a filter placed below the LED plate and is absorbed by a row of 16 photodiodes that sit next to the LEDs. This device can measure all wells in a column simultaneously, which significantly reduces the measurement time. The NEMA 17 used to run the belt and pulley system has a maximum speed of 1,000 RPM. At this speed, with a number of teeth on each pulley, the measurement system would move 0.2 of a millimeter per step. However, the wells in a 384 well plate are approximately 4.5 millimeters apart. This means that 0.2 of a millimeter movement is not precise enough to reach the center of each well. To compensate for this, a controller that can implement a half step is used. A half step will move the system 1/10 of a millimeter per pulse, which is sufficiently precise for what we're using it for. Using a half step, the system can run at 500 RPM. Based on the linear speed of the system calculated here, the entire well plate can be measured in approximately half a second if the motor is run at 500 RPM. We don't anticipate running the motor at this speed, but that's the fastest that it could measure the whole plate. Here's another view of the 384 measurement system with the photodiode array. Our next chamber measures 6, 24, 48, 96, and deep 96 well plates. We want to make sure our light source is hitting the center of each well to increase the precision of our measurements. To achieve this in one system for various well plate sizes, we had to integrate an inner well plate selection assembly. As you can see in the image, the system within the red box moves along the outer belt and pulley system in the same fashion as the 384 well plate system did. The foundation of this design is the same as the 384 measurement system. The full LED assembly moves across a well plate, measuring all wells in each column simultaneously, as described before. To ensure the light is hitting perpendicularly to each well, the well plate selection assembly was designed. This is a 3-tiered light direction system. The top plate has small through holes to redirect the LED light and transmit the number of beams that correspond to wells in a column of each well plate size. From these holes, light will emit in a cone pattern. To collimate this light, a plate with lenses is included. The separation between these two plates is the focal length of the lenses. 12 millimeter lenses are used to send 10 millimeter collimated light to the 6 and 24 well plates. 6 millimeter lenses are used for the 48 and 96 well plates. Also, the lens plate includes photodiodes to measure the reflected light for fluorescent intensity. There's a filter for this reflected light, just as there was for the 384 system. And the same diode array from the 384 system sits below the well plate in this system. The final plate just holds the filters that I mentioned before. Based on the number of columns in each well plate size, the measurement time was determined at the maximum speed, which in this case is 500 RPM because we're using the half step intervals. Torque measurements were also made to ensure the inner and outer system could be moved by a NEMA 17 motor. The conical tube measurement system is very simple. There are no moving parts in it. It's just 2 plates on either side of the tube holders with LEDs and diodes in a similar arrangement to the other measurement devices. Now I'll pass it along to Mohammed to explain our shaker system.
Sorry, thank you, Mary Alice. And to now start plate movement, there was a few customer needs that were actually looked at in particular, more so than others. One particular one was looked at was cost, as well as to ensure that that linear orbital and double orbital shaking patterns were accomplished, as well as including independent patterns for each sample that would be desired. And the way we kind of formulated and created this was through the shakers that we have created now. And the shakers that we have created now are a result of that. And so as you mentioned, independent patterns, so we utilized made them relatively small in size and made them between 290 to 250 millimeters to ensure that they'd fit in the climate control enclosures and be able to place in them. And as well, we have the linear motion assembly, and linear motion is accomplished through this system by utilizing a stepper motor. And we utilize a stepper motor in this particular situation because we wanted to utilize linear movement, but provide enough speed where the shaking speeds that were desired were accomplished. And we did this by utilizing a stepper motor that had a screw that would drive it, and we had it set to a plate. And so the plate would be utilized with the rails to allow the system to move laterally and create the linear motion. In addition to this, we also utilize, in order to create circular motion, we utilized another NEMA 17 stepper motor. And this was also utilized at its max speed, which was 1,000 revolutions per minute. And we utilized, the way we did this, we had the step motor rotating, and as it would be increasing in motion, we had the ball bearings that allowed the well plates to be in motion, and which would create the orbital motion that we desired. And from this, we would utilize both linear motion in conjunction with the circular motion to accomplish the double orbital motion that is desired. And we utilize a 20 millimeter diameter for the orbital motion, as well as I would like to explain that what we did in order to accomplish the sizing was I like to emphasize, we made it relatively small, and we utilized rubber pads at the bottom of each the shaker systems in order to create some sort of resonance and to prevent resonance and allow the system to be able to move without creating a sort of a frequency that would allow it would serve as a dampener and allowed it to prevent any motion from occurring. And from here, I'd like to pass it on to Austin for climate control.
Yes, thank you, Mohammed. So for the climate control casing, the first three needs didn't truly affect and drive our design. They affected it in terms that we wanted to maximize the lifetime and minimize the cost and the energy usage of our casing system, but they didn't drive the design near as much as having an accessible interior for cleaning did, or having varying compartment temperatures between it. The system also must be able to hold different well plates and conical tubes, and they must be interchangeable. Finally, the system must also be autonomous. And so in incorporating all this, we were able to come up with our Climatrol casing device. The materials selected for this were a 1/8 inch aluminum sheet and a 1/2 inch plate, which an aluminum was chosen for its cheaper cost when it's compared to steel, yet it's still strong enough to be to hold taped holes and actually hold the screws. It also has a higher thermal conductivity to actually help create and spread out the heat, that was created by our thermal device around the entire thing to create a more constant temperature. We also chose a 1 inch styrofoam foam, hard styrofoam foam. And that was chosen for its cheap price and its very low thermal conductivity, and so making it a great insulator. When doing a 1D steady state conduction analysis between this, it is found that if under extreme conditions, the maximum loss would be 29.6 watts in a container where the containers next to it were 4 degrees Celsius, and the maximum was 70 degrees Celsius. To ensure the design was entirely autonomous, a linear actuator was installed to move the drawer in and out. The drawer was found to have an 8-inch stroke, so that way the liquid dispensing device could reach every part of the well plate movement. Because the shaking device also creates forces on the drawer when it closed, it was found that most actual linear actuators do slide. So another device was implemented. We just simply put a pin in the drawer to hold it in place. To unlock this, it was a linear solenoid was used to retract it, which applied a voltage and retracted it in. This allowed the drawer to slide in and out by the linear actuator. And when it was pushed back into place, the voltage would be removed and a compressed spring would push back out and put the pin back into the drawer. This requires very tight tolerances, and it was actually accounted for in the manufacturing process. To talk about the thermal processes, Matteo is going to go next.
Thank you, Austin. So as Austin mentioned prior, the first few needs for the customer needs were definitely taken into account. However, for temperature control's sake, the next few needs were more needed to be more specified. So one of the needs that were really important were the fact that this temperature control needed to maintain cultures within a range of 4 degrees Celsius to 70 degrees Celsius. And this was also aided with Austin's casing with the insulation provided by the styrofoam and also the aluminum. Uniform heating was also an important need to consider, with a sensor being used to measure the uncertainty within not only the temperature, but also the condensation and the humidity within the system. And need 24 regarding changing temperature speeds specifies that this environment needs to be able to reach a culture temperature within less than 15 minutes. And so as we move on to the next slide, a sort of thermodynamic heat transfer analysis was needed in order to calculate the length of time it takes for a temperature to reach another specified temperature. In this case, regarding it was first analyzed that using a steady state approximation and using a using a graph related to the thermoelectric power generator. It was found that to change from a room temperature value of 27 degrees Celsius to a value to the lower boundary of 4 degrees Celsius, 72 watts was needed to be of heat was needed to be lifted out of the system in order to have this cooling process take effect. However, this was not as simple as this. The current state of the system is in a transient sort of state where we have heat coming in, heat flux coming in from outside of the specific temperature control system. As you can see in the diagram to the left, this is the control volume for one of the systems, and this was specified as the specific one regarding the 384 measurement device. And so we have heat coming in from outside of the casing, as well as heat coming in from the different electrical devices and other devices inside the system involving the plate shakers, as well as the optical measuring devices as well. And so this transient equation was come up with, whereas the energy is equal to, on the left side of the equation, the energy is equal to the total masses of the different parts within inside the system, as well as their specific heats, multiplied by temperature. And so, as we, given the fact that there is no heat transfer or work moving to the outside of the system, inside being positive, outside being negative, a differential equation was come up with in order to solve for the amount of time it takes for the room temperature to achieve the 4 degrees Celsius temperature. And now to the left, we have the performance curve for the TEC1 12710 thermoelectric device. And using the sort of max current value, as well as the DT on the x-axis, it was found that 72 watts was needed under steady state. However, that is not necessarily the case. And so after computing the different masses for air, fluid, and also the different parts within the system, as well as considering their specific heats, the total value is calculated as 3,700. And the work generated by the NEMA 17 stepper motors for the plate shaker, as well as the measurement system, was calculated as 453.76 watts. And this resistance total was taken into account because of the fact that the temperature coming in from outside of the specific system will fluctuate as it enters into the system. It encounters resistance from the air, as well as the specific materials such as the aluminum and the styrofoam used inside the system. So as we see on our next slide, all of this is taken into account on the left side, we have the heat sink with its dimensions. Originally, a sort of Peltier, an alternate Peltier device heatsink was used. However, it was proven that this was a lot more efficient in within the design of the heat fins themselves. And so, given the Rayleigh number, we can calculate the Nusselt number and come up with a value for the heat convective coefficient as 2 watts per meter squared Kelvin. And this is also used to find the value for the heat transfer into the system, as noted in the very first equation. And so combining together the heat transfer into the system, as well as the work inserted into the system due to the motors and other sorts of electronics, and looking at the very bottom equation, the second part of the equation is related to the heat fin efficiency of the specific heating and cooling device. And so after inserting the values and calculating, Wolfram alpha was used in order to calculate the time it takes in order for the set point temperature to be reached, which was approximately 10 minutes for this ordinary differential equation. And so with that, I would like to pass it on to gas control. Take it away, Andrew.
Thanks, Mateo. So for the gas control subsystem, there are 6 customer needs that influence it, which are shown here. As with the others, the system lifetime was to be maximized and the cost and energy usage were to be minimized. However, those didn't really drive the design as much as the needs relating to accuracy, BSL2 safety, and the automation of the system. In order to control the gas composition inside the system, evacuation by purging is employed. Not only does this gas purge introduce a new mix of gas into the system, it is also able to clear out any humidity existing. The volume of the gas required to purge each climate-controlled area is 43.52 liters. The gas control works by taking gas from existing wall outlets in the lab and carrying them through a 0.75-inch diameter air hose to each one of the 5 NEMA 4 brass body controlled valves. From the valves, each gas is routed through a gas mixing chamber. From the gas mixing chamber, a pipe nipple carries the gas into a 1-to-4 gas manifold. Each outlet of the manifold will have a 1/4-inch diameter air hose attached to it. These air hoses will carry the gas from the gas manifold into each climate-controlled area. The gas will enter the area using a pipe coupling with the other end of the pipe coupling attached to a fine pore diffuser. The coupling will also be sealed around the outside with caulk to assure that each climate-controlled area is airtight. Gas is released from the climate-controlled system using a pressure-activated valve. And now I'll pass it off to Andrea for the cap removal system.
Thank you, Andrew. So one of the customer needs was that we needed to prevent cross-contamination. And because each of our well plate shakers is within the climate control system, we need to provide a way to prevent any spillage from the well plates or tubes as they were being shaken. So in order to do this, we created a device that removes both the conical tube caps and well plate lids. And so it's compatible to both. As mentioned before, a cap is attached to the well plate lids prior to the experimentation so that this device can pick up the well plate lids using the same mechanism. The way this device works is that there is a spring-controlled grip that expands as this device is pushed onto the caps. And this spring was designed in order to mimic the pinching force of a human hand between the thumb and your index and middle fingers. And so the force required was 87.23 newtons, which was found through a study as the average force, pinching force for men and women aged 20 to 94 in a study conducted by the University of Wisconsin-Milwaukee. And so using this force and a set displacement, the spring constant was found and used to determine the spring dimensions. And so once the gripper grips onto the caps on the tubes or the well plates, a NEMA 23 stepper motor is used to twist the caps off or simply lift it off. And so this device is positioned using an ultrasonic sensor, and it is connected to our material transport system so that it can move in the X, Y, and Z axis in order to accurately position itself over all of the conical tubes and well plate lids. And once these lids and caps are removed, we have a storage holder that holds all of them while the well plates and tubes do not require shaking during experimentation. So next I will pass it to Gabby for liquid dispensing.
Thanks, Andrea. For the liquid dispensing subsystem, there were 12 customer needs identified to directly affect this subsystem, with the first 3 being overall customers' needs needing to be considered for the overall assembly, such as system lifetime, which was maximized, system costs and energy usage, which were minimized, and with the next 9 pertaining more directly to this specific subsystem. So for porosity and material reactivity, we referenced other designs that work in a similar environment to ensure that the material we chose would not be porous for the substances it was handling, and a material reactivity chart was referenced to ensure the material chosen to handle the substances would not cause any chemical reactions. Fluid addition and subtraction capability is autonomously controlled through a NEMA 17 motor in conjunction with a position sensor. For no aerosol and dispense rates, motor specifications were referenced to ensure that it can achieve both the minimum and maximum dispense rates specified in the customer needs, and the volumetric flow rate was referenced to ensure that no aerosols would be created. For fluid volume, the disposable pipette tip attached was a 5,000 microliter disposable pipette tip, which can deposit both the minimum and maximum fluid volumes needed. No cross-contamination was considered using the disposable pipette tips, and I'll go in more depth on the next slide. And dispensing precision and dispensing accuracy were also used using motor specifications and the geometry of the system. So on the next slide, you can see the overall design used for the liquid dispensing subsystem, including the NEMA 17 motor, which is attached to a lead screw to create linear movement from the rotational movement of the motor. This presses down or lifts up the plunger, which creates positive air displacement to allow the substances to be withdrawn or dispensed without cross-contaminating the actual motor system itself and only interacting with the disposable pipette tips. And then one of the calculations done to ensure that it meets the customer needs is the volume accuracy. So I modeled the disposable pipette tip as a cylinder and used the exit diameter to ensure that we could create the volume accuracy that the customer specified for this subsystem. And with that, I will pass it on to Henry to go further in depth for the material transport subsystem.
Thanks, Gabby. So for our material transport subsystem, the main customer needs that drove our design was that that our system is capable of automated liquid handling. So we had to make sure that our material transport system was able to hold the cap remover and our liquid dispensing system. And to maneuver both our liquid dispensing and our cap remover, we utilize a 3D gantry system, as this has been commonly seen in other applications like CNC machines and 3D printing. And our gantry system consists of a rack and pinion system for motion in X and Y direction, while our Z direction uses a lead screw with a coupler for linear motion. Both these systems attach on top of the linear rails with a ball bearing carriage to ensure that they travel smoothly across the rails. And to go more in depth about our rack and pinion system, our rack and pinion system is a off-the-shelf part that uses a 3-to-1 gear belt reduction for our NEMA 23 stepper motor. And this puts them at the optimal range for speed and power. And with microstepping, the rack and pinion system can achieve a accuracy of 0.0006 inches per step, which is given by our manufacturer. A spring tension mechanism is featured in the rack and pinion system, and essentially the tension in the spring will keep the gears in contact with the rack at all times by pulling up on the gear. In addition, compression of the spring will accommodate the flexion of the pinion as it travels across the rack. So overall, using a gear with 22 teeth and a pitch diameter of 25.4 millimeters, we found that our system was able to travel at about 478.78 millimeters per second. And so for our z-axis, we used a lead screw with a coupler, and this allowed for a more precise motion along the z-axis for dispensing. And attached to the coupler is a plate that holds both the liquid dispensing system and the cap remover system. And also a proximity sensor is attached to prevent any collision with other subsystems such as the climate housing, and is also used for just positioning information. So now I'll pass it on to Mateo to talk about our user interface.
Thank you, Henry. And so with the user interface, a few of the customer needs that were especially important were regarding the intuitive design of the user interface, as well as how the safety how safety measures are input into the system. And so it can be seen that there for customer need 7, an emergency shutoff is needed within the system in order to prevent the system from creating a more harmful environment for the user. And along with that, visual indicators and audio indicators are also placed into the user interface in order to make it more known that the user interface, that the different processes, what point the different processes are at within the systems. And so as we move on to the next slide, we decided to employ an iPad model with a button housing in order to control the different subsystems inside the structure and enclosure. And so the iPad is connected to a microcontroller, a Raspberry Pi, which is then used to control all of the different motors and electronics within the structure and enclosure of the entire design. There are 3 LED indicators, green, yellow, and red. Green, meaning that everything is running smoothly. Yellow, if the yellow indicator happens to appear, it means that a process is, or a subsystem control is in process. And red means that there's an error within the process that needs to be reprogrammed, or the user will be able to manually adjust it. A DAC is used for sensors and storing data. And the design's total power usage is about 407 watts, which is within the 720 allowable watts within the entire design. And so the Raspberry Pi is also connected to a smoothie board, which is then able to connect to different motors in order for them to in order to get them to function. And the Raspberry Pi is also connected to an Arduino within the measurement subsystem specifically in order to control the entire design. And the iPad is used as it is very intuitive and easily programmable. And now we'll move on to the next subsystem regarding structure and enclosure.
All right, so the main customer needs that drove our structure and enclosure design was that the exterior was touchable, so that when the user touches the enclosure, that they don't get burned by perhaps like hot temperature, and also that the weight was able to fit on top of a research benchtop. Next slide, please. And so for our structure, our overall size was 70 inches by 34 by 35. And the base of our enclosure was made of a 1/4 inch thick aluminum alloy plate. while the structural framing of the housing unit is made of a 1/8 inch thick aluminum square tubing that are welded, and they are welded onto the base plate to provide a permanent and strong joint bond. And aluminum was chosen for our material as it's provided a strong structure for our enclosure and also lessen the weight. So the casing of our enclosure is made of fastened clear acrylic glass panels, and they allow the user to see through the case to see the processes that are happening inside the enclosure. And to access our design, the user is able to open the enclosure using a door found at the front of our design. The door is attached to the casing by using a hinge and has a rubber-coated handle so that the user can flip over the door onto the top of the case. And by opening the door, the user is allowed to access the design to perform any form of maintenance, such as cleaning or replacing the weld plates. And now I'll give it to Austin to speak a little bit more about how we met our BSL2 requirements.
So the most common biosafety requirement is the class 2, A2, which is a 30% exhaust. Those use 100 linear feet per minute airflow across the entire system to continually moving it. Well, we decided to kind of go a little bit higher and to do the BSC class 2 type B2 system, which will result in 100% air exhaust through a HEPA filter. We decided on using a 105 cubic feet per minute blower to suck in the air and to blow it out through the HEPA filter out of the entire enclosed environment for 100% exhaust. To calculate how much, what the inlet size should be to find the 100 linear feet per minute, we back calculated using the cubic feet moved and the 100 linear feet per minute across to find that we need to cut a size of 32 inches by 4.75 inches across on the other side of the system to ensure that there is a linear flow moving from one side of the system to the fan blowing out to the other to ensure that all the BSL2 biosafety features were met. And now Andrew is going to talk about the final cost of the system.
Thank you, Austin. And so our total prototype cost estimate is $9,852.86. So the way we found this cost was by researching off-the-shelf parts and raw material costs through different manufacturer websites, and then utilizing the manufacturing estimated cost tables provided by Dr. Traum in this course's materials to calculate the manufacturing labor, assembly labor, and energy consumption costs. And then on to our next slide. So why choose Mecker? So we decided, so our goal was to design a bioreactor that had autonomous systems to minimize human interaction while increasing the amount of independent experiments run by creating 4 different climate control cabinets, each with their own shaker, measurement system, and temperature and gas control systems in order to maximize the time that the well plates and tubes spent inside a controlled environment to prevent any cross-contamination and any variations in the experiment. And so combine all of these systems combined under a budget of $10,000 makes our design not only fit the customer needs, but a desirable design to use in any lab. So thank you for your time, and we'll now open it up to any questions.
All right, great. Thank you for your presentation. Very well done. Let's turn it over to the panel. See if we have questions.
I have one.
Go ahead.
Your XYZ motion system, you looked like for X and Y, you guys are using rack and pinion. How much backlash are you going to have in your gearing? And is it going to cause problems with getting to the tiny 1 point something millimeter diameter wells on a 384 well plate?
We couldn't eliminate backlash completely, but to try to minimize it, we just tried using the manufacturer's spring tension mechanism to keep it closely in contact. And the manufacturer's data stated that it could achieve accuracy of the small accuracy needed.
Okay.
This is Tom Singer from Northrop Grumman. I noticed that you've got 4 separate enclosures, and they all seem sort of individually tailored to a different like well plate or tubes. And if I, as an experimenter, want to run a whole bunch of different things in, say, 96 well plates, what are my options with your system?
So you'd only be able to run 196 well plate at a time. If you wanted to run 2 different experiments on the same thing, you would have to do a 96 well plate. And then, for example, the either 15 milliliter, 50 milliliter, or the 384 well plate on the other one. It's just how we chose to design it. In theory, the design could be changed and the measurement system that allows for 96 could be reproduced, but it does significantly increase cost. So at the cost that we, no, go ahead.
Oh, I guess I was going to point out, so with your system, I can use 25% of the capacity.
If you want to run the same experiment in the same well plate size, you would only be able to use one of the climate controlled areas.
Okay. Let's see, what else do I have on my list? You have a, I'll say, significantly different sensing system than other teams seem to have had, where you are, I guess, continuously moving over the or over and under the surface of your well plates and taking readings on the fly. Is that something? I mean, certainly your motion system can support that. Is something that your sensors can support?
Yeah, so actually we accounted for stopping over each column to take the measurements. So the time that I gave does include stopping, giving the photodiodes the 2 milliseconds of response time or whatever they had said. And like I said, if you run it at a slower speed, you can give the wells more time, each column more time. If you want to still make 6.5 minutes, you only have to move it, I believe, 0.3 of a millimeter per second. So you really only have to run the motor very slowly. So if that is a concern, you can slow the motor down.
Okay, yeah. When you said, I think you said half a second to measure every well on a 384 well plate. That's, I mean, that's awfully fast. Let's see. I was also there early on. It kind of happened a couple of different places through the slides, but I'll just pick at early on when you're talking about timing. You had a precision of 0.383284 seconds, which certainly you can calculate that, but it's not useful information. Anything when you're talking about timing like that, anything under the 100th of a second is probably, even that is probably way more detail than you need. When you're talking about power and you were at like 450.74 watts, that's probably too much detail there. I saw I think 17 hertz shaking frequencies was something, or was that work out to in RPMs, about 1,000 RPMs? Is that about right?
Yeah, it was about 1,000 RPMs was the shaking frequency. It was like the Neo 17's motor's max speed was 1,000 RPMs.
Okay. Have you done any sort of vibration analysis to check if you have any natural frequencies that you're going to excite as you shake these?
So I have not completely finished my vibration calculations, but the rubber pads that I utilized that were looking into it were relatively good to be able to surpass this. But at the time, I didn't finish the calculations, if I'm being honest.
Okay, I got one more before I'll let you go, and maybe some other folks can ask questions. On your drawers, you said you had a retention pin that you were needing to achieve very precise positioning to get that retention pin engaged. Am I understanding that correctly?
Yes, and so the linear actuator actually has, I believe, a 80-pound force limit to it. So we'll be able to pull it very tight to be able to insert that pin exact. So basically what I'm saying is like that force limit will be able to pull and move that to its exact position that needs to be at so that the pin can insert directly into the drawer.
Is there a better way that you can think of that maybe you don't need quite such good positional tolerance on a pin system like that?
I couldn't think of one because the whole goal is to hold it in one exact spot and not have the drawer move. And so to hold something exactly in a spot does require quite tight tolerances.
I would suggest that a tapered pin would get you the same place with a lot less precision requirement on the initial positioning.
That is a great idea. I did not think of that.
I'll let somebody else go for a little while.
Hey there, Mateo. Did you switch the Nussel number correlations?
For what exactly? Oh, I don't think I quite understand your question. Maybe if we go back to the.
Yeah, could you go back to the slide?
I think there. I believe no, the next. No, it was that slide. Yeah. Then I don't believe I.
So if I could jump in here for a second, we're looking at a bank of fins, right?
Yes.
And you've got a Nusselt number correlation that's got a Rayleigh number in it, and I realized that you and I walked through this yesterday, so I want to make sure that maybe I didn't miscommunicate something, but Rayleigh number is typically used for natural or maybe forced convection. And so was this the correlation for a heated or a cooled flat surface facing up, or was this the Nusselt number correlation for this particular fin bank?
This was the correlation regarding the surface facing up, I believe. This was for the this was initially to calculate sorry, I didn't label it as well as I could have. This was initially to calculate the non-heat fin arrangement within the steady state configuration. But then this is then replaced by the actual heat fin equation at the very below with the Seaman in that sort of specific. That's for the adjusted heat fin heat transfer equation.
I got you. Okay, so I'm gonna, with your permission, I'm gonna just draw a little bit on here if that's okay. So we're talking about this term that I'm bracketing.
Yeah, exactly. Yeah.
And okay, so I think I understand now. So this H value that you've calculated is the value if, I hate to put a big red X through this, I feel like one of my MIT professors that used to do this all the time. So this H value is the convective heat transfer coefficient if there is no fin tube heat exchanger in place.
Exactly.
And so this term that I've bracketed here in red would actually be HA delta T, where this is the H value. And what you've done by now considering this thing that I just put a big red X through, let me remove the big red X. There we go. Is replace HA delta T with epsilon C delta T. Okay.
Precisely. Yeah.
I got it. Okay.
Sorry for the confusion, everyone.
Yeah, no, that's fine.
No,
now that you describe it, it
makes
makes sense.
Yeah.
Yeah. Okay. I didn't appreciate the first time through that's what you were doing. Okay.
Yeah,
I got you now.
So I've got one question because I think I saw it was on an earlier slide. Unless I'm getting confused because I've watched a bajillion of these so far today. The total length of this thing is like 60 something inches.
Yeah, it's 70. Yeah, it's the very first slide, Mohammed.
Overall dimension, well, there we
70.
go.
Oh,
Overall
sorry.
70.
Yeah, it was 70 inches in length.
Yeah, I believe it.
Okay.
This one? Okay.
Yeah. Do you guys have a concept for just how big 70 inches is?
Yeah, it's a little, whatever, basically just about 6 feet.
Right. That's like half of a laboratory sometimes. I've actually worked in lab spaces that weren't even 6 feet wide. So there's one thing to consider. I know the customer requirement was that it needs to fit on top of a lab bench. You're getting really close to it with your size here.
Yeah, that's where we were able to find through research that the kind of larger sizes were up to 84 inches in laptop length.
Yeah. And then I guess the second thing here is, how big is a typical biosafety cabinet that one of these might go? Like, so you got, we were talking about, so you actually made the enclosure a biosafety cabinet.
Exactly. So I didn't have to fit
That's smart.
and make it our own.
I'm completely spaced on that one. That's smart. I like that. I must have missed that little bit of the presentation. Cool. Well, there goes me ragging on you guys for something. So it was bound to happen after 7 presentations in a day that I would slip up. Yeah, it still is. It's still really. So you guys have 4 independent compartments here, which is great to be able to have all those different independent experiments. But you could have gotten away with just 2 of them, and have this thing be 3 feet wide, and one of us could bear hug it that way.
We did consider doing 2, one for all the well plates and one for the both conical tube sizes. But as far as measurement went, because of the distance between the light source and the well plate in the multiple well plate size measurement systems, we really wanted to, because the well diameter in a 384 well plate is so small, we wanted the light source to be closer to the actual well plate than it could have been in the other system. So we made it independent. That's why we have the extra.
Okay.
Okay. Any final questions? We're actually right at the end of the session, so we probably have time for one more if anybody's got one.
I don't want to run over. I could, but I don't want to run over.
Oh, do it.
All right. So I'll make the comment that I've made in email, but haven't actually made in person to a whole lot of groups. A general. Well, first I'll say I really appreciate that you have needs on every system, and everything you're doing, you're tying back to customer needs. That you're one of the few groups that did it, and the only group that did it as extensively. So good job. From a concept of operations standpoint, it's a little muddy on exactly what is going to happen. When a lab environment, a lab tech hits go, what exactly your system can do, and how all of the various subsystems within it interact, what's happening at any given time, what your capabilities are to move fluid around, and that sort of thing. And the intro that you gave was good on this slide was really good, and I appreciate kind of going through what the various systems were. But I think it would be more effective from the standpoint of, hey, here is a typical experiment that a customer might want to run in a bioreactor, and here's how our system is going to do everything that needs to be done for that experiment. you kind of came close to it by highlighting all of your subsystems in the basic overview, but tie that to what a customer can do with this. More so than just, hey, we've got a system to, twist off caps, and we've got a system to, to dispense fluid. What is that going to look like in practice?
That makes a lot of sense. Very much. Thank you.
Also, just to go back really quickly, because I know we're going to run over, essentially the user should only have to place the tubes or the well plate in the system. The lids in theory and caps should be on when it gets into the system. And then from there, the system should do everything it needs. The user will also have to place a device on top of the well plate lid so that the cap holder we use can pick it up off of there. But once it's in the system, once the user places the empty plate or tubes, it should run on its own.
Man, this thing's 350 pounds too.
Yeah, it ain't moving once it's there.
Team lift.
Forklift.
Or we can just go get our toolbox and completely disassemble it.
There you go.
All right. Well, so let's wrap it up there. Let me hit the stop record button and thank group for presenting and sticking with us even a couple minutes over time.